Hi all, this is lecture 19 on engineering mathematics from the University of Notre Dame. We continue with the discussion about eigenvalues and eigenvectors. And the first topic we're going to start today will be to see the role of eigenvalues and eigenvectors in solving linear ordinary differential equations. So a little bit ahead of our time in essence, because we will be discussing differential equations on the second part of the course, but this is a good time to bring the subject in parallel with the discussion on eigenvalues and eigenvectors. So let me assume that we have to solve the following system of equations that you see on the first equation, du over dt. Equal AU. So this is a dynamical system with coefficients defined by this matrix A that contains constant coefficients, so there's no time dependence here. So we want to compute the u over dt AU. We want to solve this for u, and we want to see how this dynamical system evolves, starting from some initial state defined by u of 0. Obviously, this is a system of equations. You can see the u is a vector that consists of n components. Now, by the way, looking at this equation, and remember from the early days of calculus or your differential equations in your undergraduate studies, you can extrapolate that if u was a scalar unknown, you will say that u is e to the at times u0. And actually, we will see the same formula is applicable even in our case with u being a vector and a not being just a number, but a matrix. So let me convince you that that's the case. So we're going to try to look for solutions that have the form u of t equal e to the lambda t times x. So at this time, we don't know what lambda is going to be. We don't know what x is, but we're going to assume that the general form of these equations is u times u equal e to the lambda t times x. So if you substitute this equation on the left-hand side, you get lambda times e to the lambda tx, and on the right-hand side, you get a times e to the lambda tx. So e to the lambda t cancels out. And effectively what we get ax equal lambda x. So immediately you can see that the solution to this system of differential equations with linear coefficients has the general form e to the lambda tx, where lambda and x are the eigenvalues and eigenvectors of the underlying matrix A. So effectively, the general solution will be superposition of all the solutions of the form e to the lambda tx. So you can assume with confidence that the general solution u of t will be c1 e to the lambda 1 tx1 plus etc. cn e to the lambda n txn. So I want you to remember this general form because we're going to use it again and again in the lecture today. And if you wonder how do you get this coefficient c? Well, this coefficient c will be computed from the fact that at time t0, when all of these exponentials become 1, u of 0 is given as the initial condition u1 of 0 up to un of 0. So the general form again is u of t equals c1 of e to the lambda 1 t of x1 plus cn e of lambda n txn. And effectively, as I highlighted in the discussion on the slide, this is sort of equivalent to a more one-step solution of this system of equations, which is e to the at times u0, where somehow when you expand that e to the at, e to some metrics, you get effectively this general solution. Obviously, I'm going to have to show you why that gives me the same solution as this, but for now, this is what I want you to remember because in essence, this is what this slide has proved to be the general solution to our system. All right, So back to the same system. This is what the general solution is all about. And let me write something about the initial conditions. So if you expand the condition U0 in terms of the eigenvectors x1 to xn, and here we're assuming that we have n distinct eigenvectors and n distinct eigenvalues. So I can, they form a basis of my Rn space. So U of 0, I can write it as C1 x1 plus Cn xn, or I can write this in a matrix form as capital X times C, where capital X is the matrix with columns, each of the eigenvectors, equal to this coefficient C equal to U of 0. This U of 0 here should be a bold U. We will correct this in the posted slides, is the initial condition. And so you can see that C is X inverse times U of 0. And so the general solution that you see on this slide is completely evaluated from in all its detail. So let me do one example. So let me take a matrix A that is an upper triangular and some initial condition U0 that is 9, 7, 4. You have to trust me that if you compute the eigenvectors and eigenvalues, the lambdas come to be 1 to 3. And actually, you already know that because this matrix is upper triangular. So the lambdas are defined from the diagonal elements 1 to 3, and the eigenvectors are 1, 0, 0, 1, 1, 0, and 1, 1, 1. So you can actually see immediately that U0 can be written as 2 times x1 plus 3 times x2 plus 4 times x3. We can check this actually with the first element. 2 plus 3 gives me 5, plus 4 gives me 9, which matches that. And similarly, you can check that you get the 7 and the 4 that you see in your initial conditions. So with this U0, and knowing the coefficients C1 to C2 to C3, you can write down that the general solution is 2 times CT x1 plus 3 times CT2 e to a power 2 tx2 plus 4 times c to the power 3 tx3. And a completely known solution to this, completely evaluated solution to the system. And as I mentioned before, keep the long perspective that the solution that you see here is basically exactly equivalent to what you expect to get if A was a scalar, in which case you write e to U of t being e to the at times U0. So you still have the same sort of solution, but now e to the at is a matrix that somehow when you multiply with U0, it gives you this nice solution. We're going to be doing this calculation shortly, but effectively this long expression here, it's equivalent to this direct form. All right, so let me continue with another example. I'm going to take vibrations from your mechanics, from your dynamics courses. So we have a mass m oscillating with displacement from equilibrium that I denote here as y. That's a function of time. Y double prime is the acceleration, y prime the velocity, y the displacement, m the mass, b some damping coefficient, and k the spring constant. And so what I'm going to do is I'm going to utilize the machinery from the earlier slide where I had the linear system of ordinary differential equations. I'm going to have to write this second order equation as two linear equations so I can form a nice linear system with some identifiable matrix A. So the way we're going to do this, let me just go directly to the equation, and you will see exactly what is involved. I'm going to take for simplicity m equal to 1. So my system of two equations is what you see here. And if we look at the first equation, it says nothing else, but the derivative of y is equal to y prime. All right, y prime is the first derivative. So the first equation doesn't say anything new. And the second equation says the derivative of y prime, which is the second derivative, is minus k times y, as you can see from the equation, minus b y prime. So basically, with this equation, I've been able to drop the system of two equations. I'm sorry, I have been able to drop the second order one equation system to two first order linear equations of this very nice form, where now this matrix A is constant, again, by assuming that in this particular case, M is equal to 1. So you can, with no difficulty, you can actually go and compute these solutions to this system by first evaluating the eigenvalues and eigenvectors of this matrix. And again, we're going to be revisiting this when we do differential equations. And at that time, I am not going to tell you absolutely anything new, because what you will hear now, it will be actually the exact solutions that you learned when you take differential equations. So linear algebra actually is the machinery to computing the solutions to this sort of linear dynamical systems. So let me find the eigenvalues of this matrix A. So this is my matrix A. So you form A minus lambda I, which is this. So you have this nice characteristic equation. Obviously, it has two lambdas. And you can actually show that if you solve this and you compute lambda 1 and lambda 2, the eigenvectors are 1 lambda 1 and 1 lambda 2. Now, obviously, what type of eigenvalues you get depends on what numbers b and k are. So the b's can and k can result to eigenvalues that they are real. They can result to eigenvalue that they are complex, to lambdas that they are positive or lambdas that they are negative. But generally here, I'm denoting the solutions as lambda 1 and lambda 2. And you can show that the eigenvectors are 1 over lambda 1 and 1 over lambda 2. And using our general formula, I can write down that the solution is now C1 e to the lambda 1t times the first eigenvector times C2 e to the lambda 2t, the second eigenvector, and that's my solution, y and y prime. And if, let's say, the only thing you care is the solution y of t, not the velocity y prime, then here is the general formula for the solution of this particular second order differential equation. So y of t equal C1 e to the lambda 1t plus C2 e to the lambda 2t. And obviously, I hope you remember this from your linear algebra, from your differential equations course. Okay, so let me start plugging in some particular values for the damping coefficient and the elastic constant K to discuss some particular case. So in this case, I take that the damping is 0. Actually, this is wrong here. So M is still equal to 1. So we need to correct this. So the damping is equal to 0 and K is equal to 1. Okay? So, and I take for convenience that the system starts at some displacement 1 and with initial velocity equal to 0. So if you solve for the eigenvalues of this system here, what you will get, if you form if you go back to the system of the equations that I had here, 0, 1, minus k and minus b. So b will be equal to 0, all right? So k is equal to 1. So you're going to have a matrix 0, 1, minus 1, and 0. So this matrix you can immediately show that has eigenvalues plus minus I. All right, so if lambda is plus minus I, you can actually compute the eigenvectors, and you can show that the eigenvectors are 1i and 1 minus I. So here is a case where we are actually having an anti-symmetric matrix A. We can see that this anti-symmetric matrix leads to pure complex eigenvalues, and also the eigenvectors in this case are convex. But still, our formula is for the solution of the linear system of differential equations is applied. So this is the general solution that you have for our system. And if you expand these exponentials in sines and cosines, you basically get something that looks what you see here. So what basically remains now is to apply the initial conditions that y prime is equal to 1 and 0. So if you plug in this equation the time to be equal to 0, and you constrain the expressions that you get so that y at 0 is equal to 1 and y prime at 0 is equal to 1, you get a solution that if I go directly to the answer, it gives you these coefficients C1 and C2, and you can do the algebra if you want to, and you can see the general solution that you get is y being cosine of t, and the velocity y prime of t being minus sine of t. So this is literally, if you think the unit circle, it's a motion around the unit circle, and obviously there is no damping, so this motion keeps going for ever, and it's given by y of t equal to cosine of t. All right, so we have seen how this vibration type of problems can be modeled with linear system of ordinary differential equations. So what I want to do is I'm going to try to solve the same type of differential equations, but now by introducing some discretization through finite differences to simply see what the result of finite difference approximations does to this type of systems. So let's revisit the same problem. And again, the mass is equal to 1 here. We need to correct it. The damping coefficient is equal to 0. And K, the spring constant, is equal to 1. And the initial conditions for y and y prime is equal to 1 and 0. So what I'm going to do is I'm going to discretize the system. And let me go directly what type of discretization I'm going to do. I'm going to introduce some new variables. I'm going to call the displacement y as yn, capital Yn. So that's the displacement at time n. And I'm going to call the velocity y prime as zn. So that's my velocity at time tn. So un is basically the discretized version of this vector u of t that you see here. All right, so this is my discretized unknown at time n, and obviously I'm going to have to write down now the governing equations for this discretized vector, and then introduce different type of approximations to allow me to compute it as we move forward in time. So first, let me write the system of equations on these new variables, capital Y and capital Z. Remember, my system of equations is really y double prime plus y equal to 0. So let me approximate this. Let me see. This is the system of equations I have for y, capital Y and capital Z. You can see here it says y prime equal to z. So the derivative of y prime equal to z. That makes sense, right? Y prime is, if you take the, remember capital Y is little y, so the derivative of little y obviously is the variable z is equal to y prime. And also you can see z is equal to y prime. So the derivative z prime is really y double prime, which is equal to minus y from my differential equation. So basically I have written again this system with one equation, second order, to a system of two linear equations in terms of these variables, capital Y and capital Z. And I remind you again, capital Y is the displacement, capital Z is the velocity. And I'm going to write those things in a system of linear equations shortly so I can use the algebra from eigenvalues so I can solve these equations. But the first thing I want to do is I want to discretize those two equations that you see there. I want to write approximate equations that tell me how y and z at time tn plus 1 can be computed if I know yn and zn at time tn. So my first approximation that I'm going to use is what is called a forward finite difference approximation. And so you can see here, if you look at the first equation, right, there is a time derivative here, and this time derivative equal to z. So I am going to approximate the derivative with the value of time tn. So you have a zn here, and I use a forward finite difference approximation for y. So I can write this as yn plus 1 minus yn divided by delta t equal to zn. That's an approximation of my first equation. And similarly, I can write for the second equation as cn plus 1 minus zn divided by delta t is equal to minus yn. Again, this is what is called forward finite differences. I want to assume that you have seen this before. I want to assume that this is not going to be the first time, but you'll be seeing and using this a million times in your courses and research. But what you see again here is a forward finite difference approximation of the two equations that we derive from the second order ordinary differential equation that governs vibrations of a mass, as we have seen in the earlier slide. So what I can do now is I am ready to write this in a matrix form. And if you remember, we introduced this vector u that includes both y and z. So if you put this in a matrix form, un plus 1 is a times un. So effectively, you can think that you start from some displacement of velocity at time 0, and you multiply with the matrix A, and you compute some new displacements and velocities, and then you come back and you keep doing this until the time of interest. And obviously, the solution that you get depends on the particulars of this matrix, and more or less it depends on the eigenvalues that you get for this matrix. Now, I remind you from 1 or 2 slides ago, if you solve this problem exactly, you do get a solution that corresponds to a motion around the circle, right? There is no damping, so you keep moving forever around the circle. And obviously the question is, do you actually move around the circle when you discretize this with forward finite differences? So let's see what is going on. So again, this is the system. So what we need to do is we need to compute the eigenvalues of this matrix. So if you compute those eigenvalues, you can immediately see that the eigenvalues are 1 plus minus I delta t. Delta t is the time step. And you can see that the magnitude of these eigenvalues is greater than 1. And I remind you, when you write down the general solution of this system of differential equations, if you remember, is basically the eigenvalues. You get terms like C1 times lambda 1 to the power k times x1, and C2 lambda 2 power k x2. And in this case, if the absolute values of lambda is greater than 1, when you take powers of that, obviously you expect when you take 1 to something greater than 1, and you get taking higher and higher powers, but eventually that thing will diverge and go to infinity. And that's exactly what actually you get by iterating this system of equations for this particular structure with forward finite differences. So if you start, let's say, from the unit circle, instead of staying on this dotted unit circle, the solution gradually actually diverges, and you see the solution in this case after 32 time steps is not anymore in the unit circle, and it will keep getting away from the unit circle as time passes by. So this problem, obviously, it's our first encounter with something that, with an approximation that becomes unstable. And I say an approximation that becomes unstable because we know that the exact solution is supposed to be on a circle, but this finite difference approximation leads to a solution that is unstable. So, you can numerically try to solve a problem, and because you use the wrong approximations, like in our case here, for finite differences, the solution diverges, as you can see on the pixel here on the right. Okay, so let me do another type of finite difference approximation, and in this case, I'm going to use backward finite difference approximation. So the equations look actually the same as before. The only difference is that the velocity, all right, the velocity and the displacement are being approximated on the right-hand side by time n+1. Remember, my problem was that y prime equal to z and z prime equal to minus y. So the z and y on the right-hand side have been approximated at time n+1. So in essence, you can see that how from n+1 you go backwards now. You use the differences that is backwards in writing this equation. So this is a backward finite difference approximation. If you put these two equations together, you get a system that looks like this. All right, so don't forget that your objective is to compute yn+1 and zn+1 given yn and zn. So this equation is a little bit strange. If you put the n+1 variables together, the matrix A multiplies the y and z, the un+1 vector at time n+1. Really, it is the inverse of this matrix that we call A before, okay? So it is the inverse of this matrix that we call A before. Keep that in mind. So if you calculate the eigenvalues of this matrix, I see here in the notes actually that I am calling this, actually I see, okay, it's not called any name, so that's good. So if you compute the eigenvalues of this matrix, the eigenvalues are 1 plus minus I delta t, and someone will say that's bad news because the magnitude of these eigenvalues are also greater than 1, and so the solution will actually diverge, but that's not the case again because these eigenvalues are for this matrix, and really what we need is we need the eigenvalues of the inverse matrix, which is 1 over the eigenvalues of this matrix. Remember, if lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A minus 1. So if the eigenvalues of this matrix have magnitude that they are greater than 1, the inverse has a magnitude, eigenvalues with magnitude less than 1, which means in this particular case, the solution will actually spiral towards 0, 0, towards the origin. So the solution will die for this particular problem. And this is exactly what you get numerically. If you start with being on the unit circle, and you start doing some iterations on this algorithm, computing yn+1, zn+1. After 32 steps, the solution will be here, and as you keep going, eventually will spiral towards the origin 0, 0. All right. You may say, okay, one diverges, one goes towards 0, 0. Is there any better approximation? And one of the better approximations that you will learn is to use central finite differences directly on the original equation. So you remember my original equation was y double prime, the acceleration is being minus y. So if you use a central difference for the second derivative, you get something like that. And if you do similar analysis to what I show you, that I don't want to do for this equation, as it will take us a little bit away from the course, but you can show that if delta t is less than 2, then effectively the solution will stay close to the circle, and so it's stable. And here is a numerical implementation. You can see the exact solution on the unit circle, and the blue dots correspond to the central finite difference approximation that is known in the finite differences community as the leapfrog method. Bottom line, what you need to know here, right, is that we can take a second order differential equation, write it down as a system of two linear equations that we can solve together using the eigenvalues and eigenvectors of the underlying matrix A, but also we can pose this algebraic system using discrete variables and finite differences. And the message that you got from the last few slides is that you need to be very careful when you use finite differences, because depending on your approximation, some solutions stay close to the exact solution, some diverge to infinity, and some collapse to the origin. So these ideas of stability, of course, will be fundamental to some of the things we will be discussing later in the course. And remember, in the context of eigenvalues, the stability is really defined in terms of the magnitude of the eigenvalues, if they're greater or equal or less than 1. Okay, so we solve the system of equations. We discuss about the asymptotic behavior of the solution. For example, we said, does the solution approaches 0 when t goes to infinity? So in that case, obviously, the system is dissipating energy and the solution dies out, all right? And we, again, we said that the solution depends on the eigenvalues of this matrix A, because the solution consists of terms that they are of the form e to the lambda t x. So depending on the values of lambda, this term will either go to infinity or it will decay towards 0. So for sure, to have a system approaching 0, lambda needs to be negative, or at least you need the real part of lambda, if lambda is imaginary, to actually the real part of a complex lambda to be negative, so that e to the lambda t x approaches 0. Okay, so actually here is, I see the case with a complex lambda that involves a real part R and an imaginary part S. So in that case, actually, you can split the e to the lambda t as e to the RT involving only the real part, and then e to the lambda SI. So this exponential, the second, involves a cosine and a sine of lambda S, so it's an oscillatory term. So really the stability of this term, it depends on the values of the real part of lambda from this term e to the RT. Because at the end of the day, the magnitude of this complex term e to the IST remains constant, equal to 1. Okay, so so really, when we discuss stability and decaying behavior, we're either looking for eigenvalues that they are real and negative, or we're looking for eigenvalues that they are complex but have real parts that they are negative. And there is a very easy criterion to actually figure out if indeed the eigenvalues are negative or have negative real parts, at least for the simple case of 2 by 2 matrices. And we're summarizing this in the slide to follow. So for 2 by 2 matrices, we can easily discuss if matrix is stable and if the solution of du over dt equal AU decays to 0 as t goes to infinity. So let me just state the two conditions on a matrix A that will take care of the eigenvalues either being negative if they are real, or having a negative real part. So the two conditions are the following: the trace of the matrix needs to be negative, so A plus D needs to be negative, and the determinant needs to be positive. Okay, so very easy. You don't need to directly compute the eigenvalues. you compute the trace, it needs to be negative, and you need to compute the determinant, and it needs to be positive. The proof is rather simple. If you take the case of eigenvalues that they are real, so let's say if the eigenvalues are real and negative, you can immediately show that, if they're real and negative, their sum obviously is going to be negative. And you remember the sum of the eigenvalues is the same as the trace. So this first statement is taken care of. And if you take the product of the eigenvalues, if they are negative is positive, the product is also the determinant, and that takes care of the second statement that you see here. And you can prove actually the opposite as well. So if the determinant, which is the product of lambda 1 and lambda 2, is positive, so basically lambda 1 and lambda 2 have to be either both positive or both negative. If t is negative, there is no other option than for lambda 1 and lambda 2 to be negative. And that's the proof for this case when the lambdas are real and negative. Now, we also have the case when the lambdas are complex numbers. So if the lambdas are complex numbers, you can still show the validity of these two statements, that for the real part of the lambdas to be negative, the trace needs to be negative and the determinant needs to be positive. And actually, again, the proof is very easy. So if you assume that lambdas are complex, they will be conjugate to each other, so it will be of the form r plus is and r minus is. So if you take the trace of this, the trace will be 2 times r. Immediately you know that then r has to be negative, okay, for if the trace is negative. And if you take the product of this, the product is always positive because you're going to be getting r squared plus s squared. So in that case, the determinant is positive, which takes care of the second statement that you see here. So again, for 2 by 2 matrices, and it doesn't matter if the eigenvalues are real or not, a good way to check if the eigenvalues are negative or that they have negative real part is to take the trace and show that is negative and compute the determinant and show that is positive. I want to show you actually a stability diagram to see which case is stable and which case is unstable for all possible combinations of the trace and the determinant. So if you have a 2 by 2 system of equations and you form the characteristic equation, this is the eigenvalue equation, right? So what you will get here, you will get the trace, which is the sum of the two eigenvalues, and this is the product of, this is the determinant, which is the product of the two eigenvalues. So an equation always looks like this, and you can see solving for lambda involves the computation of this square root here, and depending on the value of t squared minus 4d, this number can be positive or can be negative, leading to real or complex eigenvalues lambda. So let me just summarize the schematic of stability. If I take the trace on the horizontal axis, the determinant on the top, so I am going to effectively, so I'm going below this parabola that you see here. So this parabola is t squared equal to 4d, all right? And because t here is in the horizontal axis, so below the parabola, t squared is greater than 4d, all right? So below the parabola, I am going to be getting real eigenvalues, and above the parabola, I'm going to be getting complex eigenvalues. So you can, I mean, let's pick up one of the regions. So for example, here, the square root, this t squared minus 4d is positive. So you're going to get a solution that is t plus minus this square root, okay? So you can immediately see that for positive t, all right, so for positive t, both eigenvalues will be positive, which means the solutions effectively will be unstable, all right? So both eigenvalues will be positive, so the solution will be unstable. In the other side, you're going to have, if t is negative, the eigenvalues below the parabola will be obviously real. They will be negative, and the solution is stable. And above the parabola, you're going to get complex eigenvalues. So the real part in this region will be positive, so the solutions are unstable. Here, the real part will be negative, and the solution will be stable. And here are some examples. So in this case, this matrix leads to stable situation. You can actually see that the trace here is negative, and if you actually go and compute the determinant, so the determinant of this matrix will be 0 minus the minus 2, so it will be equal to 2. It's positive, all right? So the trace is negative, and the determinant is positive, so this is a stable situation. In this case here, the trace is negative, but if you compute the determinant, you get a negative determinant, so this is unstable, and this is a case of a neutral situation. And again, I remind you the two criteria, if I can go back, for 2 by 2 matrices to get negative eigenvalues or eigenvalues with negative real parts, the trace has to be negative, and the determinant has to be positive. So this is a very nice way to actually demonstrate graphically all the possible scenarios. This is a stability diagram, and later on for differential equations, we're going not only to plot a diagram that looks like this, but also in the different regions. So how does the solution of the differential equation behaves? Here we are only looking at the behavior of the solution as time t goes to infinity. Okay, so again, we started with the simple vibrations problem, and we saw a case in the approximation with finite difference where the solution diverges, it goes to infinity. We saw a case where the solution decays to 0, and then we saw a stable solution where we remain around or close to the circle at all times. Okay, so let me continue, and we discussed that the general solution to the system of differential equations du over dt is equal to au. The general solution was e to the at times u0. So I need to say something about what is this exponential of a matrix. So I need to show you where the exponential of a matrix as a matrix comes, and I want you to think of a Taylor series expansion. So if you can define powers of a matrix and you accept this to be a convergent expansion, a convergent series, then I can define e to the at being this nice expression. And the only thing you need is for these powers of a to exist, which they do. Okay, and so this is the exponential of a matrix is defined by this nice expression. By the way, if you have other convergent expansions, you can also go and define other functions of A using convergent series. So you can come up with interesting functions of a matrix A, similar to what you see here for the exponential. If you take derivatives of this equation with respect to time t, using common sense type of calculations, what you will get on the left-hand side, obviously, symbolically, this derivative will be a times e to the at, okay? Notice that both a and e to the at are matrices. And on the right-hand side, you're going to get an a. Here, there is an a squared, so you're going to get 2 times a t squared, so 2 and 2 cancel. And similarly for the third term, etc. I want you to immediately see that I claimed before that that the solution of my differential equation was e to the at times u0, and you can plug this equation to our differential equation, and indeed convince yourself that this expansion with this derivative satisfies the differential equation. Okay, so if you really want to write in a compact form the solution to our differential equation du over dt equal au, you're just going to write e to the at times u0. And I think that expression should become maybe at the end of this slide. Let me say something interesting about the eigenvalues of the exponential e to the at. So if you look for the eigenvalues, because you know the eigenvalues and eigenvectors of A. Remember, A and A squared and A cubed have eigenvalues lambda, lambda squared, lambda cubed, and they have the same eigenvector x. So you can immediately see that the eigenvectors of the exponential e to the power at is still x, the same as for the matrix A. And actually, you can see here, this thing inside parentheses is e to the lambda t. So the eigenvalue of the exponential of a matrix, so e to the at has an eigenvalue e to the lambda t. This is very nice. So e to the at has an eigenvalue that has eigenvalues that they are of the form e to the lambda t. And again, this is the general form of our equation. And this solution is actually correct, even if we have a shortage of eigenvectors even. So if we don't have n independent eigenvectors, this expression still in this form is correct, okay? Its evaluation may be a little bit different from what we will do in the lecture today, but this formula, it's applicable even if there is a shortage of eigenvectors. Okay, so let me proceed to the case where A has n eigenvectors that are item in this column matrix in this eigenvector matrix X. So the matrix A can be diagonalized, as we have seen in the earlier lecture, as x lambda x minus 1. And so what I'm going to do is I'm going to take this expression for A, and I'm going to plug it into the exponential e to the at. And so if you do this term by term, the I can be written as x inverse. At is x lambda x minus 1t. Here you have an a squared, so that's x lambda x minus 1, x lambda x minus 1, etc. And if you put all of this together and you cancel this x inverse x, and you put x and x inverse outside the parentheses, what you actually get is you get a factorization that looks like similar to the factorization of A. The only difference is you have x e to the lambda t x minus 1. And by the way, this is not surprising, because I already, this lambda matrix has in its diagonal the eigenvalues lambda 1 to lambda n, and I already told you that the eigenvalues of e to the at are e to the lambda t. So this exponential, this e to the lambda, capital lambda t matrix is basically a diagonal matrix that contains in the diagonal e to the lambda 1t, e to the lambda 2t, etc. Okay, so I'm going to write this actually explicitly. So if this is the solution, if this is e to the at, the solution to my differential equation will be e to the at, which is this, times u0, all right? And actually x minus 1 u0 are this, coefficients c1 to cn that we had seen earlier coming from the superposition of the solutions. So I can write my general solution as the matrix X that you see here, which is the eigenvectors in each of the columns, times the matrix C to the lambda T, which is this diagonal matrix, C to the lambda 1T to the lambda NT, times X minus 1 U0, which are the coefficients C. There was no space here to write explicitly X minus 1 U0, but you remember the initial condition says that U0 is C1 X1 and Cn Xn. So effectively, this coefficient C this is the X matrix, so this coefficient C are X inverse times U0. So X inverse times U0 are the coefficients C defined by the initial condition for my problem. So again, what we have done is we defined the exponentially to the at, we defined the general form of solutions given by this wonderful expression that you see here. It involves, it factorizes basically the exponential. The eigenvectors are the same. What changes are the eigenvalues, but now go to the exponent and you get e to the lambda 1t, e to the lambda nt as the eigenvalues of the matrix e to the at, and the eigenvectors remain the same. So let me consider some examples to see different situations of this. And in particular, I want to see how all of these things work when we have a shortage of eigenvectors. So a case where somehow we don't have n eigenvectors. Can I actually use this sort of expression? So here is the simple system, y double prime minus 2y prime plus y equal to 0. So I can write this with my standard notation for my vector u being y and y prime. I can write this as a system of a linear system of equations with the matrix A being 0, 1 and minus 1, 2. Okay, hopefully by now you know how to do this easily. So if you compute the eigenvalues of this matrix, you will see that it has two repeated eigenvalues equal to 1, and you can test that the sum of these two eigenvalues, you get the trace 2, and if you take the product, you get 1, which is equal to the determinant of this matrix. So really there's no other the eigenvalues are the same, and if they're the same, the only eigenvector you can compute is the eigenvector 1, 1. So you can see actually that 1, 1 is an eigenvector with an eigenvalue 1. So in this case, the diagonalization of the matrix A, as we noted from the earlier slide, is not applicable here because we only have one eigenvector. So the question is, how do you compute actually e to the power at for this particular case? So I'm going to try to show you actually on the general form of solutions for this system. And again, when we later on we discuss about differential equations, you will be amazed that somehow we're going to get the same answer many weeks from now. So again, I want you to foresee that linear algebra is the tool to learning differential equations. So let me do the following trick. We want to compute the exponential. So I am going to subtract I and also remove an e to the it term out. I is the identity matrix. So e to the it actually is the same thing as multiplying this second matrix with a scalar e to the power t, okay? And I can approximate this matrix e to the a minus it with the Taylor series expansion. And when you look at the Taylor series expansion, you may think that I dropped the quadratic, the cubic, and the other terms, but actually have dropped nothing, because all the other terms in this particular case, they are equal to 0. I'm inviting you to take this matrix A, compute A minus I, and compute A minus I times A minus I. So A minus I squared, just to see that A minus I squared is 0. And if A minus I squared is 0, the third power is 0, the fourth power is 0. So this expansion that you see here is correct. Okay? So e to the at is written as e to the power t times this matrix. And now I can actually use my general solution that says that u of t is e to the at times u0. All right? And I can use this expression here and write my solution for y and y prime as e to the t I times a minus I. So this is a. If you subtract I, you're going to get minus 1, 1, minus 1, 1. That's what I have, times t times the initial condition y0 and y prime 0. So if you solve for y of t, you get e to the t times y of 0 from this identity, and then you get minus t e to the t y0 plus t e to the t y prime of 0. So you can see that the solution now doesn't simply involve the exponentials that we had seen before for e to the t, but now there is a term, these two terms that are t times e to the t. You may have memories of this from differential equations, right? So if you have repeated eigenvalues, actually you have to try solutions that they are not just of the form e to the lambda t, but also solutions. The second solution will be t e to the lambda t times x, and this is exactly what we get in this second and third term that you see in here. So this is very nice case showing that the expression for e to the at times u0 is also applicable if you actually have repeated eigenvalues. Okay, so let me do another case. Let me take this dynamical system with an A being an upper triangular, some initial conditions. You can actually write these initial conditions as the sum of the two eigenvectors. For this case, the two eigenvectors are 1, 0, and 1, 1. The eigenvalues are 1 and 2. So the eigenvalues are distinct. The eigenvectors corresponding to this are 1, 0, and 1, 1. So the solution will be our classical standard solution. There are the coefficients C1 and C2 that you need to have for the initial conditions are equal to 1 in this case. You can actually see at times 0, you get 1 and 1 equal to 2, and you get 1, so you satisfy the initial conditions. And you can actually put this in the most general form that I had before, the e to the at times u0. So I can write actually the solution also as x. X is the matrix of the two eigenvectors, 1, 0, 1, 1. And x inverse will be 1, 0, minus 1, 1. Okay. And then e to the lambda t will be also diagonal matrix with on the diagonal having e to the lambda t. So e to the t for the eigenvalue 1 and e to the 2t for the eigenvalue here equal to 2. And if you do the multiplication, you get basically that your matrix e to the at is this upper triangular matrix that looks like this. So A was an upper triangular, e to the at comes to be, no surprise, an upper triangular matrix that looks like that. And actually you can see immediately the two solutions here are the same, right? So, you know, the initial conditions that I have plugged in in this expression were 2 and 1. So if you put u0 equal 2 and 1, you're going to get 2 of at plus e to the 2t plus et. Okay, so let me see, is that correct? So, okay, I see the bottom is correct, e to the 2t. It will match that. But if I put u of 0 being 2 and 1, so I'm going to have 2 of this and 1 of this 3 plus 1. I am wondering if this here has to be equal to 2. So for t equal to 0, okay, how about if you check this, and I'm going to check it also at the end of the lecture in case something has been missed. So basically this expression here needs, for u0 equal to the initial conditions, it needs to directly match what we got explicitly. So this to me looks correct, because at time 0 you have 1 and 1 equal to 2, and at time 0 no, actually, wait a second. This is okay. So u of t, okay, yes, and at time 0, then you get 1, okay. So something is needs to be checked in that particular case here. Okay, so but for sure this e to the at matrix is upper triangular, okay, and follows basically the structure of this matrix A. So let me take a matrix A now that is anti-symmetric, and you remember for anti-symmetric matrices, the we anticipate a particular structure that so if you go and actually compute the eigenvalues and eigenvectors, you'll be able to use any of our general equations for e to the at to solve the system of equations du over dt equal au. But what I want to do is I want to explicitly go and compute a squared, a cubed, a fourth, and you can see the pattern on these matrices. And if you keep continue computing a to the 5th, a to the 6th, a to the 7th, a to the 8th, you realize that these matrices repeat themselves. So a to the 5th, a to the 6th, a to the 7th, a to the 8th will be a repeat of a squared, a cubed, a 4. And that actually can be used in a very nice trick to approximate the exponential e to the at through a Taylor series expansion by computing the appropriate. So all of these matrices are 2 by 2, right? So you can use the appropriate components of these different matrices, a squared, a cube, given by the expressions that you see here, to compute all of the contributions from the Taylor series expansion. So for example, if you want to compute the element 1, 2 of this matrix C to the AT, so the 1, 2 contribution from I will be 0. From matrix A will be 1. So 1 times t, so we're going to have a t there. From matrix A squared will be 0. From matrix A cubed will be minus 1, t cubed over 6, etc., etc. So if you do this algebra for these 4 terms, you will immediately see what you get is you get the expansion of a cosine of t for the 1, 1 term, an expansion for the sine t for this term, minus sine of t and cosine t for this term. So e to the at for this matrix is this interesting matrix that is also anti-symmetric, okay, and has this interesting structure given in terms of cosines and sines. So you can be asked to do lots of different type of calculations like this, right? So, I mean, what is interesting with this particular matrix here, so this matrix is anti-symmetric, and the exponential you can see is orthogonal matrix. So if you go and compute the eigenvalues of A, they are obviously complex conjugates. Actually, you can see immediately minus lambda. The eigenvalues of this will be plus minus I, all right? So the eigenvalues of e to the at is really e to the it and e to the minus it, and that's from where you get cosines and sines, okay? So I can see this slide actually summarizes some of the things I just mentioned. So in general, okay, just remember some facts. The inverse of e to the at is e to the minus at. The eigenvalues of e to the at are e to the lambda t, where lambda are the eigenvalues of A. And the case we just mentioned, that if A is anti-symmetric, e to the at is orthogonal, and its inverse then is the same as the transpose, which is e to the minus at. Okay, so in this case, basically, the matrix A has pure imaginary eigenvalues plus minus I, and the eigenvalues of e to the at are e to the it and e to the minus t, which basically have a constant magnitude equal to 1. So in this case, we have neutral stability, basically, and pure oscillation with no dissipation of energy. So the magnitude of the solution remains unchanged, okay? So this is what we call neutral stability, basically. Okay, so the solution in magnitude, it doesn't change. I mean, it's like rotating around the circle, so the vector of the solution changes, but the magnitude remains the same. And all of this results from matrix that, this particular matrix that is anti-symmetric. Okay, so let's keep moving forward, and I want to say a few things now in summary for symmetric matrices. So let me first summarize them again. So for symmetric matrices, we have n real eigenvalues, and the eigenvectors can be written down in an orthonormal form. So we have n orthonormal eigenvectors q1 to qn. So when we diagonalize the symmetric matrix, effectively the Q inverse, we used to have a general matrix X here for the eigenvectors. Now, to emphasize that that matrix X is orthogonal, we put Q, and we know for orthogonal matrices, Q inverse is the same as Q transpose, okay? Something that we will discuss, and I will show you this with examples also. For symmetric matrices, you can show that the number of positive eigenvalues is the same as the number of positive pivots. So that's a very interesting statement here that connects basically the pivots with the eigenvalues. And as a matter of fact, you can immediately see that a matrix S, a symmetric matrix X, will have all its eigenvalues positive when all the pivots are positive. And as we will see, we will use this as a definition for positive definite symmetric matrices in another lecture. But for now, the number of positive eigenvalues is the number of positive pivots. Now, we mentioned this 2 slides ago, that if the matrix A is anti-symmetric, has pure imaginary lambdas, and basically the eigenvectors are orthonormal, but they're complex. Okay, so we still have for this case of anti-symmetric, we still have orthonormal eigenvectors, but they are complex. So for complex matrices, so all of these things are for real matrices. I'm not going to elaborate too much about elements A that have complex elements, but for complex matrices, if we have a matrix that has elements that are complex numbers, the classical test that we have seen here for symmetry as being S transpose, it is actually for complex matrices changes to S being equal to S conjugate transpose. So when we refer to symmetry in complex matrices, we refer to matrices S that are equal to S conjugate transpose. So for example, this matrix here, if you take simply the symmetric part of that, is not, you can see you're going to have a minus I here and an I there. But if you take the conjugate symmetric part, then you can see S is the same as S conjugate transpose. And this is what we refer to symmetry, to symmetric matrices for complex matrices. So this particular matrix has eigenvalues 1 and -1. And this particular matrix again, this other matrix that you see here, that it is anti-symmetric, has complex numbers, right? But you can see if I take the symmetric, it looks the same, and if I take the conjugate, I'm going to get a minus I here and a minus I there. So A is minus A conjugate transpose. So this is what we call an anti-symmetric matrix when we work with complex matrices. So symmetry, I just wanted to give you this as heads up. Symmetry and anti-symmetry for complex matrices required to have, in addition to the transpose in the definitions, they require to have also the conjugate element here. So symmetric means S equal S conjugate transpose, and anti-symmetric means A equal minus A conjugate transpose. Okay. All right. So let me go back to these ideas of symmetric matrices leading to real eigenvalues and orthonormal eigenvector basis, and try to expand and possibly try to prove some of this. So we are looking for symmetric matrices. So for symmetric matrices, we already said that this X, I mean, you can, this expression that you see here, it is applied, right, for, I can use it for any matrix that has distinct eigenvectors, right? So if it happens that this matrix is symmetric and you take S transpose of this expression, what you will get is X minus transpose lambda. Lambda remains as is because diagonal times X transpose. So immediately you can see here for a symmetric matrix, X minus inverse has to be X transpose. So really that matrix X becomes an orthogonal matrix, and that's why we denote this expansion, this diagonalization for symmetric matrices. We denote it as Q lambda Q transpose, because Q inverse is equal to Q transpose. So we don't use X for the case of symmetric matrices. We emphasize that X is an orthogonal matrix, so we use Q instead. And the facts basically that we have for that case of symmetric matrices is that it has real eigenvalues, and the eigenvectors are orthonormal. So this is a very major statement for symmetric matrices, and lots of times the expression that you see in here, this Q lambda Q transpose for symmetric matrices, you will see it in the literature written down as what is called the spectral theorem. So the spectral theorem, it's not clear. So let me just write it. So the spectral theorem is, it says that the symmetric matrix can be written as the product of an orthogonal matrix times a diagonal matrix Q transpose. But if you take the columns of capital Q to be Q1 to Qn, and the eigenvalues to be this diagonal matrix to be lambda 1 to lambda n, you can write this matrix as lambda 1 Q1 Q1 transpose plus lambda 2 Q2 Q2 transpose, etc. And effectively, that's what we refer to as a spectral decomposition. So effectively, you can see the spectral decomposition as the process that diagonalizes S to this matrix lambda, or also you can see this as the process whereby representing the matrix S in its eigen component form, and I refer here to Q1 Q1 transpose, Q2 Q2 transpose. Then effectively we have decomposed S to this rank 1 matrices written down using one eigenvector at a time in the form Q1 Q1 transpose times lambda 1 and lambda 2 times Q2 Q2 transpose, etc. That's the spectral theorem. Okay, and again, the spectral theorem, it's this diagonalization of any matrix by representing it in this eigen form implied by the equation that you see on the middle of this slide. All right, this theorem comes with other names in in physics. So you can imagine, since you start with a matrix A and now you diagonalize it, so this is known in applications as the principal axis theorem. It's like finding some new representation of the matrix A where now that we call it a principal axis representation where the matrix becomes diagonal. All right, so we're gonna now have to prove actually that for a symmetric matrix, the eigenvalues are real and the eigenvectors are orthogonal, right? And these, the proofs are not very difficult, and we're going to try to highlight how you do this. And also we will discuss or highlight the proof, at least for the case when the eigenvalues are repeated, to see if we can say anything about the spectral theorem in that case. All right, so so the theorem basically, the spectral theorem will allow repeated eigenvalues, but to prove basically that you have real lambdas and an orthogonal matrix Q, it's easier to make that proof when there are no repeated eigenvalues. So we're going to try to prove things for that case, and then maybe highlight a few things for the case of repeated eigenvalues. Okay, so let me do an example first before we do any proof. If this is a symmetric matrix, you compute the eigenvalues, you get 0 and 5. You compute two eigenvectors, you can immediately see that they are orthogonal. The eigenvector corresponding to lambda equals 0 obviously is in the null space of A. And the eigenvector corresponding to the eigenvalue lambda equal 5, you notice is 1, 2, which belongs in a column space, which is a little bit weird, right? Because you anticipate, things from the fundamental theorem. You anticipate to get something in addition to the eigenvector that's in the null space, to get something from the row space. but the other eigenvector here is in the column space. Well, this is not a paradox actually, because this matrix is symmetric, so the column space and the row space are identical. So effectively, nothing is strange in this particular case. All right, so this matrix has two eigenvalues, but they are real. They are they are distinct. The eigenvectors are orthogonal, and you can actually diagonalize this. So you can what you can do is take these two vectors, first normalize them, and form the matrix capital Q. And I can see here we have put the two eigenvectors as columns of the matrix capital Q, normalized by this factor 1 over square root of 5. And you can, when you do the calculation, Q transpose as Q, you do actually get the matrix lambda of in the diagonal with the two eigenvalues, which here is 0 and 5. Okay, so in this case, for the symmetric matrix S, the lambdas are real, and the eigenvectors are orthogonal to each other. So let's try to prove this for the case of distinct eigenvalues. So we're going to show that the lambdas are real when we have a symmetric matrix. So let's see how this is going to work. So we are going to take the eigenvalue problem as x equal lambda x, and let's assume that the eigenvalue lambda can be complex, so it can be of the form alpha plus IB, where A and B are reals. So the conjugate, complex conjugate of lambda then will be A minus IB, okay? And we're going to assume similarly that x can be a vector, the eigenvector can be corresponding to lambda, can be complex, and we will denote the complex conjugate x as x bar. So what I'm going to do is I'm going to start with Sx equal to lambda x. Okay, so again, S is symmetric with real elements, and I'm going to take the conjugates of both the left and the right hand side. So S is real, so it's not being touched. X becomes x bar. Lambda can be, we said, can be complex conjugate, you remember, and x will become x bar. All right. And if I take the transpose of this equation of the middle, I'm going to have x bar transpose S equal x bar transpose lambda bar. Okay. So keep in mind this equation. I'm going to make a use of this equation. Okay. So what I'm going to do is now I'm going to take the eigenvalue problem as x equal lambda x, and I'm going to multiply it with x conjugate transpose. So let me do that. I'm going to multiply this with x conjugate transpose. So I'm going to get x conjugate transpose as x equal lambda x conjugate transpose x. So that's one equation. And a while ago, I derived this equation. If you look at these two equations, the left-hand sides are identical. So the right-hand sides have to be the same. And if the right-hand sides are the same, and we assume the eigen vector not to have a zero length, you can see that for this to be equal to 0, the only way is for lambda to be equal lambda complex. So basically, lambda has to be real. Okay, so that's the end of the proof. Basically, if we have a symmetric matrix that has, we basically prove that the eigenvalues of the symmetric matrix have to be real. So now, what we can do is we can go to the one step further, and we can prove that if we have a symmetric matrix that has proved real eigenvalues, we have to prove now that if we take two eigenvectors that correspond to do different eigenvalues, we need to show that these eigenvectors are orthogonal. And remember, for now in these proofs, I'm assuming I don't have repeated eigenvalues. So again, here we need to show if we take two different eigenvalues, we need to show that the two eigenvectors are orthogonal to each other. And the proof is easy. Take an eigenvector x corresponding to lambda 1 and eigenvector y corresponding to lambda 2. Multiply this equation with y transpose, multiply this equation with x transpose, and subtract the two equations. And then effectively what you are going to get, you're going to get lambda 1 minus lambda 2 y transpose x equal to 0. And because we're assuming the two eigenvalues to be different from each other, the only way for this to be true is for y transpose x equal to 0, which means that y and x are orthogonal to each other. All right, so that's for symmetric matrices, and here is another simple example that looks to some interesting way to look at things of 2 by 2 matrix. So it's a symmetric 2 by 2 matrix. You can show that the eigenvectors of this matrix are written in the form that you see here. I think I had used this type of form for 2 by 2 before. You can actually verify this right away, that if the eigenvalues of lambda 1 and lambda 2, the corresponding x1 and x2 look like that. And you can actually see if you take orthogonality, without actually having to compute lambda 1 and lambda 2, you can actually, you're going to have b times lambda 2 minus c plus b times lambda 1 minus a, all right? So if I remove b outside, I'm going to have b times lambda 1 plus lambda 2 minus a minus c. And this is equal to 0 because the sum of the two eigenvalues is always the trace. So basically, you can show the orthogonality of the two eigenvectors without actually having to compute the eigenvalues explicitly for this 2 by 2 matrix. So this is sort of a cute result that you may want to keep in mind. All right, so let me, for a second, let's move a little bit away from symmetric matrices, and let me take any real matrix S, okay? And so again, the matrix S contains real numbers, and so this is my eigenvalue problem. And we proved in the earlier slide that if S is symmetric, the eigenvalues are real, and we proved that the eigenvectors are orthogonal. The question is now, what happens if I have a real matrix but is non-symmetric? Okay, so let's consider a non-symmetric matrix, and I'm going to take a matrix A that is non-symmetric and write down the eigenvalue problem as AX equal lambda X. All right, this is my eigenvalue problem, and I'm assuming that A has real numbers on it. So conjugate, if I take conjugates of this equation, the conjugate of A is still A, then I have X bar, lambda bar, X bar, okay? So so you notice that in this case, so we started with a matrix A with lambda as an eigenvalue and x as an eigenvector, and now we have ax bar equal lambda bar x bar. You know what that means? That if lambda is an eigenvalue and x is an eigenvector of A, then lambda bar and x bar are also eigenvalues and eigenvectors. And you know that means basically that eigenvalues and eigenvectors for real matrices come in conjugate pairs, and this is what this slide summarizes. So if you have an eigenvalue that is A plus IB, you also, the conjugate eigenvalue, A minus IB, is also an eigenvalue of A. And if X is an eigenvector, then X bar is also eigenvector of this matrix. And I'm going to show you one example for this nice matrix A. So we consider A, and you can show that lambda 1 and lambda 2 are conjugate, of course, to each other as anticipated. And the two eigenvectors are actually 1 minus I and 1I. And if you want, you can actually verify that. So 1 minus I and 1I, obviously, they are conjugate of each other. And you can see the eigenvalue problem is taking care. Here, this is the eigenvalue lambda, and here is lambda bar. That's the conjugate of lambda, and that's the conjugate of this eigenvector. Okay. So again, this is a rotation matrix, a simple example to show that eigenvalues and eigenvectors come in conjugate pairs. Obviously, in this case, the magnitude of the lambdas is equal to 1. We have seen this in, I believe, the first lecture on eigenvalues. So for a rotation matrix, the magnitude of the eigenvalues is equal to 1. Okay, so that's a general statement that you can use from now on. Okay, so we discussed symmetric matrices. We took matrices with real numbers, and we saw that the eigenvalues and eigenvectors come in pairs. We saw for symmetric matrices the spectral theorem. So let me, I mentioned the different forms of the spectral theorem. So what I want to do is actually write it on the form that I mentioned it before. And I do this for 2 by 2 matrices. So if I have a symmetric S, I can write this as Q lambda Q transpose. You can see here Q lambda Q transpose, and you can see I have these rank 1 matrices. So I'm decomposing basically as the summation of these rank 1 matrices, and defined as QQ transpose, and with the coefficients on the front being the eigenvalues lambda. So this is literally what we call a spectral decomposition of a symmetric matrix S. And obviously, you can write this for any n by n symmetric matrix as shown in the equation here on the bottom. Now, if you have an n by n matrix and you compute its eigenvectors, obviously they form a basis that you can use to express any vector in that space. So if I have any vector v, I can write it in terms of the eigenvectors as you see here. And because these eigenvectors are orthogonal, they are actually orthonormal, they have also magnitude 1, you can, if you take the dot product, let's say, of the left and the right hand side with Q1, Q2 with Q1 dot product will give you 0, Q1 with Q1 will give you 0, Q1 with Q1 will give you 1. So you can see that X1 is V dotted with Q1. So effectively, any vector V can be written as in this form, where the coefficients are basically the orthogonal projections of V to each of these vectors Q. And we already have seen this. We revisited this multiple times when we discuss about orthogonal matrices, and also, when we were discussing about least squares approximations. Now, this concept of decomposing a vector on its eigenbasis the way that you see here is obviously going beyond matrices, and actually you can use literally the same idea, and you can decompose a function on an eigenbasis or eigenfunctions that can be finite or infinite, okay? And they can be orthogonal exactly as we discussed for symmetric matrices. And here's an example. If you have a function f of x, you can write this as an eigenbasis of that consists of the functions 1, cosine of x, sine of x, cosine of 2x, sine of 2x. This is what we call a Fourier series. And the basis functions that you use to define the basis here are really orthogonal. And what orthogonal means, if you take the dot product appropriately defined between these functions, you will get zeros, except when you dot product each function with itself. So the only thing we need is we need to define what exactly do we mean an inner product or a dot product for this function space. So this depends, of course, on the applications. And for Fourier series, when we use periodic functions, and here is the definition of functions with a period 2 pi, we can define the dot product between functions f and g as this integral from 0 to 2 pi of f times g. So with that definition, you can show that the basis functions we used before, they're orthogonal. So if you take, let's say, the inner product between sine and cosine of x, you can see immediately that it comes to be equal to 0. If you take, so for example, if you want to compute, just so we can see how you do orthogonal projections, if you want to compute this coefficient alpha 1, what you can do is take inner product of the left and the right hand side with cosine of x, then cosine with sine of x will give you a 0 when you integrate them over 2 pi. They will give you 0 here and there, and also with a constant term. And what you will get is you will get a non-zero term from this, which would be alpha 1 times pi. So when you multiply this with cosine of x and you integrate over 2 pi, you get alpha 1 pi, and that would be the integral of f of x cosine of x dx. So effectively, you can compute all the coefficients. So here is the expression for alpha 1, all right? You can compute all the coefficients the same way that you do orthogonal projections in the case of matrices that they are symmetric. So Fourier expansions, they are not very much different from these orthogonal projections that you learn from linear algebra. So in principle, I can say we have covered Fourier expansions, and we don't have to go back to it. But in reality, if we have time, there is much more to talk about Fourier expansion. So that's a subject we will need to come back to it in a later lecture, possibly at the end of the semester. Okay. All right. So let me, for symmetric matrices, let me make a connection between pivots and eigenvalues. And one of the statements that I gave you before was the number of positive pivots is the same as the number of positive eigenvalues. Okay, so for example, I can say that if I have a symmetric matrix that has all its eigenvalues positive, this can only happen if all the pivots of the symmetric matrix are also positive. Okay, so the proof of this is a little bit esoteric. So I want to highlight it the way Strang's textbook has this for a simple 2x2 matrix. So let me take a symmetric 2x2 matrix, that's a symmetric 2x2 matrix, and start with an LU decomposition, LU factorization of this matrix. What I have done from the matrix U, I split it to a diagonal matrix with its pivots 1 and minus A, and then this L lower triangular matrix and L transpose as you see here. So in this problem, the number of pivots, the pivots are 1 and minus 8, so one of the pivots is positive and one of the pivots is negative. So what I'm going to do is I'm going to do a numerical exploration here I'm going to take this coefficient 3, and I'm going to gradually start reducing it towards 0, so that this matrix L here becomes the identity matrix. So I am going to, while I'm moving this matrix to the identity matrix, this diagonal matrix D will remain exactly as is. So the pivots are not being touched, right? So we will, as we change this matrix L, the matrices we will get will still have pivots 1 and -8. Okay, they will not be touched, but I will push this matrix by moving slowly 3 to 0 to become an identity matrix. And in that case, when L becomes the identity matrix, so when L becomes the identity matrix, the matrix I, D, I transpose will also have eigenvalues 1 and -8. Okay, so we'll also have eigenvalues 1 and -8. So now remember, as I move 3 to 0, the pivots don't change, which means that all the matrices that I get, okay, all the matrices that I get are non-singular because the pivots, none of the pivots is 0. Okay. Now suppose that the matrices that I get as I reduce 3 to 0, that somehow suddenly the eigenvalues of the matrix switch signs. So one of them goes from positive to negative. If that happens, then at that instant, the matrix that I will get will have to be singular, right? Because I'm going to get lambda equal to 0. But none of these intermediate matrices can be singular because the pivots are 1 and -8. The pivots never change. Okay, so the bottom line is the eigenvalues that I get, okay, don't switch sign, okay, and the argument effectively can be extended beyond this simple 2x2 matrices, and you can apply this to matrices of any sizes. Again, the trick works here by doing this LDLT transpose factorization, keeping D constant, so keeping the pivots constant, and then observing what happens to the eigenvalues as L goes towards I. The eigenvalues cannot change sign, and they cannot change sign because if they do, one of the resulting matrices will become singulars, and that is not possible because the pivots are non-zero. Okay, so that's a proof basically of the fact that the number of positive eigenvalues is the same as the number of positive pivots. And if you take the extreme case of that, if you have a matrix S with all eigenvalues positive, then all of its pivots have to be positive. And as we will see, we will use this for discussing later on and trying to see if matrices are what we call positive definite or not. All right, so symmetric matrices, the pivots and the lambdas have the same size, same signs. And if a symmetric matrices has all the eigenvalues positives, then all the pivots need to be positive as well. I think there's nothing new on this slide, so with confidence we can pass it through. All right. One of the things that I want to do now is go back to the spectral theorem and address one of the silent points, if you like, that we try not to bother about, and that had to do with the fact that we assume that for symmetric matrices we had a set of distinct eigenvalues. If you remember, that was the main assumption that led basically to us proving that the eigenvalues are real and the corresponding eigenvectors to two distinct eigenvalues, they were orthogonal to each other. So the question is, what happens if we have repeated eigenvalues? And And we need to bring this issue because we had an example for non-symmetric matrices where repeated eigenvalues imply effectively a shortage of eigenvector, which means in that case we could not, use the spectral theorem. We could not diagonalize the matrix. So the question is, what is happening with symmetric matrices? And the good news are the fact that even if you have repeated eigenvalues, you will never have an issue with insufficient number of eigenvectors to diagonalize the matrix. So that is not an issue. And we would like to at least highlight two different proofs that you can follow to rigorously prove that the spectral theorem for symmetric matrices will be applicable even if you have repeated eigenvalues. So the equation that you see on the top is basically something that is we're going to take it as a valid decomposition, if you like, even when there is a shortage of, even if there is, repeated eigenvalues, because even in that case, we're not going to have a shortage of eigenvectors. Now, before I highlight two different proofs, let me just say that a theorem that is sort of a more general version of the spectral theorem, where we diagonalize a matrix, is another theorem that goes under the name of Schnur theorem, where instead of having a diagonal matrix, effectively, we are triangularizing a matrix. So effectively, we have a decomposition that looks very much like the spectral theorem. So A equal Q times T times Q inverse, where Q is a set of orthogonal, it's a set of orthogonal columns of orthogonal eigenvectors. But if I can call them eigenvectors, but the matrix T is a triangular matrix. So effectively, we have a decomposition that looks similar, but that decomposition is applicable even when you have repeated eigenvalues. And we will highlight that one of the proofs that the spectral theorem is applicable when we have repeated eigenvalues comes directly from this Schnur theorem, because if the matrix A is symmetric, you can actually show in a trivial fashion that this matrix T, it is really a diagonal matrix. All right, so all symmetric matrices can be diagonalized, even if we have repeated eigenvalues. So here is sort of one little proof. Start with a symmetric matrix that has repeated eigenvalues, and then what you do is go and add in the diagonal of the matrix S these numbers C, 2C, and NC, where C is a very small number. So effectively what you do is, by adding these small numbers in the diagonal, you separate the repeated eigenvalues. Okay, even if C is extremely small, the eigenvalues, you can imagine how it's going to look like. They're being separated, which means if they're separated, you can find a complete set of orthonormal eigenvectors. And once you do that, you can take the limit of C going to 0, and you can obtain n orthonormal eigenvectors that correspond to the original matrix. So you can do this even if the original eigenvalues were repeated, okay? So that way, basically, you will have at the end of the day a diagonalization, even for the case of repeated eigenvalues. The other proof that I gave you is based on this Schnur theorem. So let me state the Schnur theorem, and I'm going to state it directly for matrices with real numbers on them. So if you have a square matrix A, you can factor it as QT, Q inverse, where T is an upper triangular, and Q is an orthogonal matrix. Now, if you want to extend this to general non-real numbers, then this Q transpose equal to Q inverse, you have to write it as Q complex conjugate transpose equal to Q inverse. But what we're interested here is that this decomposition leads to an upper triangular matrix T. It doesn't lead to a diagonal, but you can, the proof of this theorem says that the matrix A can have repeated eigenvalues. So you have this decomposition even if one eigenvalue repeats itself a few times. So what you can do is, if you want to prove that the spectral theorem for symmetric matrices is still applicable when you have repeated eigenvalues, you can actually take this theorem and apply it to matrices say that they are symmetric. So if you apply it to matrices say that they are symmetric, you can, so if A is a symmetric matrix S, you can write this T as being Q transpose S Q. So you can just take Q and Q transpose on the other side, if you like, and identify what T is. And then by taking the fact that S equal to S transpose, you can prove that T is equal to T transpose. But T is an upper triangular, so it basically has to be a diagonal matrix. All right, and this is what I have, I believe, on this slide. So more or less what we just discussed. This matrix T, you can write it as Q transpose as Q. So if you take the transpose of this, the transpose of that will still be Q transpose S times Q. And because, again, S transpose is equal to S, T transpose will be equal to T, and T has to be diagonal. Bottom line, so we are clear on this matter. If you have a symmetric matrix, you can actually diagonalize it, even in the case of repeated eigenvalues. This is the message here, even in the case of repeated eigenvalues. Now, if you have repeated eigenvalues for non-symmetric matrices, then it is very possible that you will have shortage of eigenvectors, and in that case, you will not be able to diagonalize this matrix. Okay, there is another way for computing eigenvalues, and that is very common actually in problems in mechanics and variational methods, and where you proceed by computing one eigenvalue and one eigenvector at a time. And it is actually an important numerical calculation, because in problems with very big matrices, maybe you don't really care about all the eigenvalues and eigenvectors. Maybe you care about the eigenvectors that corresponds to the highest eigenvalues. So let me just highlight before we finish this lecture on possibly how this methodology works. So you can prove actually with a very, very simple one-line calculation that the largest eigenvalue, lambda 1, can be computed as the maximum of this ratio that you see here of x transpose x divided by x transpose x. Okay, so if you take the optimal of this, all right, you can show that you do get lambda 1 and the corresponding eigenvector to lambda 1. The question is, how do you get then the second largest eigenvalue and the corresponding eigenvector? Well, you also continue maximizing x transpose x. The only thing you have to add in the optimization is the constraint that the new eigenvector has to be orthogonal to the eigenvector corresponding to lambda 1 that you just computed. And then you keep going like this until you have computed the eigenvalues and eigenvectors of interest. There is, again, lots of benefit to be able to compute only the largest eigenvalues, or the largest maybe 2 or 3 eigenvalues and eigenvectors, and that comes very handy in lots of applications in modeling dynamics of structures and related topics. By the way, this procedure is also same, is applicable as well for problems related to what we call singular value decomposition, which is sort of a generalization of an eigenvalue analysis, and we will revisit this. And for singular value decomposition, we actually have to compute eigenvalues and eigenvectors of A transpose A and A transpose, which are square matrices even when A is not squared. And for that type of calculations, we can use this analysis that you see on this slide. Okay, so let me finish here this very long lecture, and we will on Friday with on this general topic of eigenvalues and eigenvectors. And I think the next topic for us to discuss will be symmetric matrices that they are positive definite. Until then, good study.